Okay, so hopefully you get the idea here with either the sphere or a flat plane. We can take these charges and sort of reflect them around in a way that produces a simpler problem to solve. And so now let's do one more example here, and we'll do an example of separation of variables. And I'm going to do another sort of Cartesian XYZ sort of problem, but we'll just use a different set of boundary conditions just so that we can see another kind of situation where we would end up with having to use separation of variables. And so here is our setup here. So we'll have our axes. So we have our x-axis here and our y-axis here. And just like last time, we're going to have a bunch of metal, a bunch of planes that will be all sort of connected together. So we're going to have a plane that sort of looks like this. But it continues off in this direction here. And then we're going to have another plane that goes off and continues off in that direction as well, right? And so these are, the blue are infinite grounded planes. And so that means, since they're grounded, we know that V is going to be 0 on those. And so last time, actually, let me make my colors consistent from last time. I think I used my green for those other strips. There's Y, there's X. And we have, so again, we have our two metal planes, and those are set to 0. But now, this time we had, for the previous one, we had sort of the spine of the book that's green. And so that's what we have here. We have this spine of the book. And now for this one, to make it a little bit different, instead of having it go off to infinity to the right, we're going to kind of cap it off at the other side. And we're going to have something that kind of looks like this. And so we have these insulated strips where the potential is equal to a constant. We'll just call that constant V naught, right? And so let's just put a bit of geometry here just so we know. Let's say that this is at y equals 0. So we're sort of, the bottom is at y equals 0. The top blue plane is at y equals a. Y equals a. And then the two sides, even though I didn't draw it quite nice and symmetrically, we'll say that this is at x equals b, and this is at x equals negative b. So it's sort of symmetric along the y-axis there. Okay, so before we start doing any kind of math, let's sort of write down the boundary conditions so that we know what we're working towards. And so I'm just going to kind of label these. Remember, we should have, remember the Laplace's equation is a second derivative. And in this case, we're going to have to deal with derivatives in x and y. So we should have two x boundary conditions and two y boundary conditions. And it's kind of easy to see we sort of have the top, bottom, left, and right. So those will be our boundary conditions. So the first one, let's do the two y boundary conditions first, because those will be easier to deal with. So remember, a y boundary condition means we know the potential at a value of y. So x can be anything, but we're looking at the, actually, let's be more exact about that. We'll say that at y is equal to 0, we know that the potential is 0. Okay. So that's our first boundary condition. Our second boundary condition, that's at the, so that the first one's at the bottom plate, second one's the top plate. So at y equals a, the potential is also 0. So those are our two boundary conditions for y. And now I need two boundary conditions for x, and those are just these two green strips, right? So I have b at x equals plus b, again, any value of y. That's going to be that constant b naught. And then I have b at x equals minus b, again, any value of y, and that is also b naught. So I have two boundary conditions for x and two boundary conditions for y. Okay, so now we do separation of variables. So I'm using the Laplace equation that says del squared v is equal to 0. And since I'm talking about a two-dimensional situation, I have second derivative of v with respect to x, partial derivative, plus second partial derivative with respect to y is equal to 0. And so if you remember, we made this assumption that the potential as a function of x and y is going to have a particular form. And that is that it's going to look like all the x stuff by itself multiplied by all the y stuff by itself. So I have sort of x of x times y of y, right? So I have the x stuff and the y stuff separated out. And then we're going to go through the same exact procedure we did last time. So I'm going to kind of skim through this a little bit. So what we're going to end up with, remember, we plug in this new assumption into here. We can pull out a y for the x derivative and then x for the y derivative. And what we end up with is an equation that looks something like this. So we get something like that, right? And just like before, this stuff is x only, and this stuff is y only. And by doing that, if I have a whole bunch of stuff that only depends on x and a whole bunch of stuff that only depends on y, the only way that I can add these up and make sure that they're 0 all the time, no matter what value of x I pick, no matter what value of y I pick, I can only do that if these are both constants. And again, I'm going to pick the constants in a way that kind of will make the math easier in a second, but I can certainly pick something like this, where the x part is k squared and the y part is minus k squared, right? Last time we sort of moved the y to the other side and we set them both equal, but in this case, this is the x part and this is the y part. That's not meant to be a fraction. Oops.